Warning: the video you're about to watch contains mathematics at the level of pre-calculus. All material has an assumed prerequisite of college algebra and trigonometry. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is just a continuation of our review of trigonometric functions from the unit circle approach. You should have just watched the video on a review of unit circle and special triangles, and now we're just going to continue this with talking about reference numbers. This is the last kind of idea before we step away from just playing with the unit circle and start talking about trigonometric functions. So what is the reference number? Well, let t be a real number. The reference number associated with t, which we're going to call t bar, or sometimes I actually use t hat, to be honest with you. I just didn't have the font for it, but t hat is the shortest distance along the unit circle between the terminal point, determined by t, and the x-axis. I'm going to show that with a previous example, one we finished in the last video. In the last video, we were given an arc length t equals 5 pi over 6. And the terminal point defined by t equals 5 pi over 6 was this point over here, negative root 3 over 2, comma, 1/2. But I used, during the problem, I used this other length called pi over 6. Notice that other length, called pi over 6, is the shortest distance between that terminal point and the x-axis. It's the shortest distance between the terminal point and the x-axis. So that is defined, that distance that I'm kind of really highlighting there, I guess, that distance is defined to be the reference number. So this would be t hat, or t bar, whichever you prefer. That number is going to be critically important for your success, whether you're using the unit circle approach to trigonometry or right triangle approach to trigonometry. In the unit circle approach, it is called the reference number. In the right triangle approach, it's called the reference angle. And I will commonly just switch into calling it reference angle almost all the time, just because of a habit that I have. But that is really the basic idea. Draw out your arc length t, and then figure out what's the fastest way to get to the x-axis. That fastest distance along the arc to the x-axis is called your reference number. So let's try this out in an example. Find the reference number for each of these arc lengths. So we have an arc length of 5 pi over 7. Each time you see this, it's a little helpful to draw out a unit circle. It is a unit circle, not that you have to write in 1, 0, but I'm going to just to accentuate that. And you're carving out a path along the unit circle in the counterclockwise direction, because t is positive, and that path will be of length 5 pi over 7. Well, a lot of people don't know, let me use a different color here. A lot of people don't know how long that path is, 5 pi over 7. And the way you can determine that is to note, if you had gone all the way around to this edge right here, that length would have been pi. I'm going to write that in. So that just landing right there would have been pi. Now, our denominator for the length we're looking at is 7. So I'm going to write pi with a denominator of 7, multiply top and bottom by 7. So that length, had I just landed on that negative x-axis, would have been 7 pi over 7. Which means that, had I highlighted to this point right here, it would have been half of 7 pi over 7. So I'm going to write this as, even though this is an improper way of writing a fraction, I'm going to write this as half of 7 pi over 7, 3.5 pi over 7. Well, the number we're trying to get to, the length, is 5 pi over 7. So it's somewhere between 3.5 pi over 7 and 7 pi over 7. So So somewhere in this quadrant 2, I'll just stop maybe right around here. So this is t equals 5 pi over 7. And I'm going to go ahead and erase that 3.5 pi over 7 because it's terrible notation. You shouldn't use decimals within fractions. All right. Drawing this was not the question. The question was, what's the fastest way to get to the x-axis? What's that fastest distance? Well, if you know that to get all the way around to that x-axis is a distance of pi, which is 7 pi over 7, and you've only gone 5 pi over 7, then it should make sense that you still have a little bit to go, specifically 2 of those pi over 7s to go. So that is our reference number, 2 pi over 7, because you didn't go the full 7 pi over 7. So in this case, t hat is equal to 2 pi over 7. Let's do it again, but this time with a negative distance, because we haven't really investigated that. And I kind of want this negative distance. Well, we'll go ahead and deal with that. So here is our unit circle. Again, not beautiful, but it works. 1, 0. Since t is negative, we're going to go clockwise around the circle. And I'll start it up. It starts going along this edge of this circle, lazily kind of carving it out. And it wants to get to a negative 7 pi over 9. Now, had I rotated all the way to here, it would have gone a negative pi, which is a negative 9 pi over 9. Notice how I'm constantly looking at these denominators to kind of get my value of pi in terms of that denominator. So did we go a full negative 9 pi over 9? No. We did not go a full negative 9 pi over 9. We only went a negative 7 pi over 9. Let me get the right color in there. So let me just showcase the arc that we're kind of going along. So it probably ends right about here. You're basically dividing this half circle into 9 segments, and we only went 7 of them. So this point right here tells me I've landed at an arc length of negative 7 pi over 9. The remaining distance I should have gone, if I wanted to land at the x-axis the fastest, would be our t hat, our reference number, which is a distance of 2 pi over 9, which, by the way, brings up a very important point. So let me label this first. T hat is 2 pi over 9. And now I'm going to go back to the previous page here where we define this reference number. And I'm just going to make a little note. Our reference number will always be considered as a positive number. We will not worry about what direction we're going to get to the x-axis. All we're worried about is what is the actual distance. So that's critical to note because reference numbers are never negative. There we go. All right, so let's go ahead and finish out that example. The very last example on this page showcases something that usually throws people off. So people often think that distances along the arc of a circle have to be in terms of pi, but that's not true. It's just a distance. I could say, what if the distance is 0.1, or in this case, what if the distance is 5? Well, I'll still draw out a unit circle. There we go. And I know we're heading in a positive direction because t is positive 5. So we're going to go counterclockwise along this unit circle. Remember, if we make it all the way through halfway, we've gone a distance of pi, which is 3.14 and some change. But we want to get to 5, so we're definitely beyond pi. The question is, how far beyond pi? Like, if you go all the way around, we know that distance is 2 pi, which is approximately 6.28. So that's not really how far we want to go. The big question is 5 going to stop in quadrant 3, or is it going to stop in quadrant 4? And my advice is really to think in terms of what pi over 2 is. If we had only gone a distance of pi over 2 to this distance right here, well, that's approximately 3.14 divided by 2. What is that? 1.5 5 maybe, roughly. 1.55. Very, very roughly, right? So if you think about pi over 2 being 1.55, very roughly, it's not exact, okay? But if you think about it being that way, then getting to pi, which is 3.14, if you add another little quarter length, which is 1.55 roughly, again, plus 3.14 is 4.6, maybe 4.7, but it's not exactly 5 yet. So we need to go even a little bit more. And here we go. We're now likely somewhere at the right spot. So that distance, t, is 5. That's how I would do it. Now, the real question here is, what is the reference number? What's the fastest way along the arc to get to the x-axis? Well, we could highlight that. That's actually fairly easy. Highlighting that it's just this distance right here. But the question is, how do you find that? Well, that's actually not too bad. Think about it in terms of mathematics. If I told you from beginning to end is a distance of 2 pi, right? But then you said, oh, I didn't make it all the way to the end. I only made it this point right here, 5. I only shaded all that. What's the remaining distance? Well, it's just right minus left, 2 pi minus 5. That's what our reference number is going to be. That length, actually I should draw that in blue, shouldn't I, just to keep it. That length is going to be 2 pi minus 5. And often, that's a perfectly fine way to leave your answer. Of course, you're more than welcome to grab a calculator to do that, but let's suppose that you're working on an exam and your instructor does not allow you to use calculators on exams. Well, then you should probably know just to leave that as 2 pi minus 5. It's roughly 1.28, but I would probably leave it as 2 pi minus 5. There you go. So that's how you can find the reference numbers pretty quickly. Now, there's a lot of different ways these questions can be asked, and so I decided to throw in one more question here to really showcase the flexibility of where you need to be. So suppose that the terminal point determined by t is 3/5, 4/5 on the unit circle. Well, I'm going to just graph that out really quickly. So here's our unit circle. Again, forgive my sloppy circle. Actually, that wasn't too terrible. It's been worse. How's that? And we know that we have the point 1, 0 on there, but we're told that we have a landing point or a terminal point of 3/5, 4/5. I know it's in quadrant 1 because they're both positive. And so therefore, our arc length, t, is this distance right here. That's t right there. Find the terminal point determined by each of the following. So let's take a look at this. Find the terminal point determined by each of the following. Pi minus t. I'm going to use that same unit circle to really showcase. So had we gone all the way over to pi, we would have landed here. But that's not what this is asking. This is asking, what if you landed at pi, minus t? So we got to pi, but then we have to subtract off a distance of t off of this. Notice I'm using blue, that's on purpose. So here I am, I land right there. Again, I want to just reiterate that this distance I'm highlighting in yellow is actually pi minus t. But due to symmetry, you can see it very easily here. Due to symmetry, the y values are the same height, 4/5. The x values, they're equal and opposite of each other. So the x value on the right is 3/5, so the x value here is a negative 3/5. They have the same reference number, and so their ratios are the same. That is going to be a theorem we're going to state later, but it is true here. So that's how you could do that problem. Very nice problem. Well, what about negative t? What if instead of going upwards by t, we went down by a distance of t along, again, the arc of this curve? So we go down here a distance of t. I want to make sure that I keep it somewhat symmetric here so you can see. Yeah, I think that's pretty good. And you would label this point down here. Notice this is definitely a distance of negative t, because the distance above is positive t. And there's a lot of symmetry here as well. The x values will be the same, right? 3/5. The y values will be opposite. So the y value for this is 4/5. Therefore, this will be a negative 4/5 because it's in quadrant 4. And that would be the terminal point for negative t, 3/5, comma, negative 4/5. Now, a lot of students want to memorize this stuff. I highly recommend you don't. Instead, I highly recommend that you just use logic the entire time. That will pay you back dividends in the long run. Now let's take a look at this last example. What about 2 pi plus t? There's two ways to think about this. I kind of like to think of this as you get to t first, and then you add another 2 pi. That's kind of how I visualize it. And this time I'm just going to wreck my curve here. So I will rotate through a length, starting at 1, 0, rotate through a length of 2 pi. Here I go, just going through a length of 2 pi. Remember, that's actually the circumference of the unit circle. So that means I'm rotating through the entire length of the unit circle. By the way, I said I would go to t first and then rotate 2 pi. Well, I'm actually going through 2 pi first and then I'll rotate by an additional t. Sorry about that. So there is a full 2 pi. And from there, I'll add another t. And notice when I do that, I land at that same point, 3/5, 4/5. So basically what I did is I rotated all the way around plus an additional t. And the terminal point for that is 3/5, 4/5. Let me write that down. 3/5, 4/5. All of this is important to get used to. The fact that you're rotating and using reference numbers, all that fun stuff along the unit circle should be familiar to you. It may have been a semester, but again, it is assumed that you've seen all this stuff before, so I don't really have to spend too much more time on it. I think that this is good as we have it, so we'll just leave it here.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.